Hi guys, let's continue our look at reactions of epoxides. Previously we introduced the idea of making Grignard reagents and alkyl, or could be considered aryl lithiums, because it doesn't have to be just alkyl groups. The carbon that we're dealing with here could be an sp2 carbon, and thus it could be an aromatic ring carbon. Just briefly, remember an alkyl halide will undergo a reaction with magnesium metal, oxidation state of 0, to give a so-called this would be an alkyl magnesium reagent, but these are called Grignard reagents because Victor Grignard is the chemist that first recognized this reaction and also recognized how Grignard or his new reagents reacted. They reacted as if they're essentially carbanions here. We talked about that. Here it's shown sort of covalently. If you show it ionically, we're going to have a magnesium 2+, of course. That's balanced by the bromine becomes bromide minus, and the carbanion here. This is the key thing, and it reacts as a nucleophile. Now, alkyl lithiums or aryl lithiums and Grignard reagents are always shown covalently. We learn in Gen Chem that, group 1, group 2, always ionic. Actually, that's not always the case. There is a continuum between fully ionic and fully covalent. Okay, so they're always going to be shown covalent, but consider them ionic because that lets you recognize this carbanion, and it's going to be the reactive nucleophile. One other thing I wanted to add is when the metal sort of reacts here, it's called an oxidative addition. Of the metal, oxidative addition. The magnesium undergoes or does an oxidative addition to this alkyl bromide because the magnesium went from oxidation state of 0 to now 2+. The metal has been oxidized upon adding to this alkyl bromide here. Many metals can undergo oxidative addition. In advanced courses you may learn about palladium metal undergoing an oxidative addition to an alkyl aryl halide, and actually that type of chemistry won 2010 Nobel Prize, if you want to look that up. Palladium catalyzed chemistry, and the first step in the catalytic cycle is the palladium undergoing an oxidative addition to a carbon halogen or pseudo-halogen bond. Magnesium is most common at the introductory stage, introductory level. You can also do it with lithium. Of course, with lithium, since lithium is group 1, it's just going to be monovalent here, and we talked about that. The fate of the halide is to team up with a second lithium, and so you actually need 2 equivalents of lithium. Ultimately, you need 2+, but down here the magnesium, 1 magnesium supplies the 2+. And we have used N-butyl lithium before. This would be N-propyl lithium. N-butyl lithium, we actually used it right up here as a base. So carbanions can also be used as bases. You can actually buy N-butyl lithium, okay? But now we know how to make it. That would be butyl bromide or butyl chloride or something. Okay, the halogen can be chlorine, bromine, or iodine. All right. Let's react some of these reagents. I'm going to do the second one here. Let you do the first one. Maybe we'll look at it in class. Okay, we have iodobenzene, magnesium, THF, common solvent. Okay. Ether solvents are known to be good for formation of Grignard reagents or organolithiums. Okay. I called it an alkyl lithium, but that's specific. And then I said, well, aryl. If we call it an organolithium, then it implies alkyl, aryl, or any organic. But diethyl ether or THF are common solvents for when you make Grignard reagents or organolithiums. Usually moving forward, I'll probably just refer to Grignard reagents because they're so common, but that also will also apply to organolithiums. So, iodobenzene magnesium, THF. This looks like making a Grignard. The magnesium will do an oxidative addition, and that will give us the magnesium and iodide. Okay. Shown covalently there. Of course, the benzene ring is often abbreviated as phenyl and pH, and thus we could maybe show that like that. Phenyl magnesium iodide. Of course, when you see this, we consider it as the carbanion there. And so we can consider this as a benzene ring with one of the carbons being a carbanion. All right. Again, I'm showing it fully ionic. It's probably sort of somewhere in between ionic and covalent, but it reacts as if it's the carbanion. Now we throw in an epoxide here, and the strong nucleophile will react. Strong nucleophiles always react by SN2. Yeah. Okay. And thus we're going to attack the least substituted carbon, kick the leaving group off, kick the oxygen off of the least substituted carbon. So these electrons are going to bond over here, and these electrons move on to oxygen, and that's going to give, okay, here's your two carbons of the epoxide. The leaving group leaves, the oxygen is now, see, it's in the plane, straight up. And it becomes minus. It takes on a third lone pair. This carbon has an ethyl and a methyl. Nothing changes there. We did not do any chemistry with that carbon. We just pushed that oxygen off of this carbon. And the benzene ring is down. Okay. I can bond a benzene ring there. Or I can also just say phenyl. Okay. And the methyl gets pushed up. Still forward, but here it's positioned down forward, now it's up forward. And so we have SN2 with inversion here. And so that SN2 gives that. The benzene carbon was your nucleophile, and we ended up with nucleophile carbon-carbon O. Nucleophile carbon-carbon O. All right. But this O minus picks up a proton from appropriate workup, a separate step. At this point, if we throw in, what would be appropriate workup? That would be like H plus or water. Previously I used water, but we could throw in some dilute hydrochloric acid. Then these electrons will take the H. This is a strong base. That looks like hydroxide. And we will get our final product. Just have to redraw it with an H there. Here I'll draw it with the benzene ring. Okay, that's going to be OH, ethyl, methyl. Draw that methyl, And then the benzene ring, phenyl, okay? But if you want to draw out the benzene ring, we can do that. I did it both ways, okay? Very often the benzene ring is abbreviated as phenyl. The only difference here is we have now protonated the oxygen anion, and here's your final product. Okay, right there. The benzene ring carbanion reacted here. It kicked off that oxygen, but we have to pick up a proton. That's going to have to be from workup. All right, because if there was any proton around when we had the Grignard reagent, it would have just reacted with the proton. You cannot have a proton around with strong carbanions. Again, our product here, nucleophile carbon-carbon OH. That's what we said over here, yeah? Nucleophile carbon-carbon OH. Now the carbons may have other groups on them. Okay. You can try, be working on the one above. So those are going to be carbanions other than acetylide anions. Acetylide anions can be readily made by acid-base chemistry from the terminal alkyne. These are other types of carbanions made by an oxidative addition approach. Okay, other strong nucleophiles that will react with epoxides include amines. Take this epoxide, react it with ammonia here. The amine is considered a strong nucleophile even though it's a neutral nitrogen. It's not super strong. It's not as strong as a Grignard carbanion, but it's still considered strong. So it's SN2. These electrons react at the less substituted carbon of the epoxide, kick the oxygen off. That arrow movement will give, okay, up here we have a methyl going back, and the oxygen that gets kicked off is coming forward. And it now has 3 lone pairs and is now a minus. Now down here, the oxygen was forward on that carbon, and so the ammonia comes in backside. It's going to be back, and so you would have nitrogen, but there's 3 H's here. And so this SN2 gives that there. This needs a proton to go neutral. Unless we do something else. Most commonly is to supply a proton. Now, previously we had to come in and add either acid or water. Okay? In this reaction, we have a proton built in because this nitrogen needs to lose a proton. And this is the first time we've done a so-called proton transfer, H+. And we will do this many times throughout the semester. And proton transfer will give our final product, and it will be just like we did above. We're going to protonate that oxygen, but the nitrogen will lose a proton. Proton will get transferred to there, and I'm just going to show that condensed, okay, in H2. And there you go. Now, let's talk about proton transfer. Again, we'll do that a million times this semester. It's the H+ is being transferred from this nitrogen, which looks acidic here, it's positive, to this basic oxygen. Now, it's probably between two different molecules. It's probably intermolecular. We could show these electrons taking the H and these electrons moving on to nitrogen to become that lone pair. But it's probably involves multiple molecules, and we can show the NH3 of another molecule, another one of these, and we can show the O minus. I won't show stereochemistry. Okay, so really there's three molecules here of this, three of these. And these electrons take the H, these electrons stay behind. And so we see how this becomes neutral and the nitrogen takes on a lone pair. Now, right here, this could be just that oxygen, or, okay, there's 1,000,000 in the flask. But what I did right here, I'm just going to repeat. But these electrons take an H, these electrons move on to nitrogen. And if we focus on this molecule, you see that this one now has a lone pair there, but the oxygen now has bonded to the H. And that's how we get this product. Now, this is going on millions of times in your flask. You have millions of molecules of product, but in terms of just one molecule, there's your one molecule product. Okay? And so this is most likely intermolecular. We will always just say H plus transfer. I'm not going to show an internal mechanism when it's likely intermolecular. We'll just say H plus transfer, and you need to understand how we got from this molecule with two charged atoms to this molecule with both atoms being neutral. Okay? So, again, we can't just forget about this idea. That's probably about the fifth or sixth kind of statement or general idea that we'll repeat over and over. Remember others? Anytime you make a pi bond, kick off a leaving group, easy to do. Okay. There were other things in earlier lectures. So, reaction of this epoxide with ammonia gives this product. By the way, this reaction is going to be regioselective. Yeah, because the ammonia is only going to react at this region, at that carbon, or preferentially will react there. This is also going to be enantioselective. That is, we're only going to get one enantiomer here. That hopefully makes sense. I mean, how would we get anything else here? How would you change the stereochemistry at this carbon up here if no chemistry took place there? So it is enantioselective, and thus it's stereoselective, which is a more broader term. Should be familiar with some of these terms in Organic 1, or from Organic 1. There we go. Okay, same applies to up here. This reaction up here was also regio and enantioselective. All right. This one here, I'll let you do on your own. Okay, it's two-step, starting with an alkene. Yeah. We also have other strong nucleophiles, other than amines or Grignard reagents. What's the nucleophile here? Well, it's the methoxide. right? And potassium plus. There's your strong nucleophile, an oxygen anion, and methanol is just going to be solvent. It would be a weak nucleophile. Okay, if you have a strong and a weak nucleophile, the strong one is the one that's going to react. Okay. Next topic, use of epoxides in multi-step synthesis. All right. We will do a good bit of multi-step synthesis throughout the semester. This is our first maybe official look at it. Epoxides are a great source of 2 carbons and an OH. Remember, nucleophile, carbon-carbon OH. Right? Repeat. So if you see a product that has carbon-carbon OH in it, think, if you want to go backwards, think what type of nucleophile could have reacted with an epoxide to give this product? This is terbutylene. It's a compound used to treat or prohibit premature labor in women. It has hormonal properties. But I see a carbon-carbon OH. Now the carbons are going to have to be sp3 carbons, okay? Because the carbons of an epoxide are sp3. So this carbon wouldn't count. But here I have carbon-carbon OH. And I have a nitrogen. We know nitrogen is often a nucleophile. So nucleophile right here, carbon-carbon OH. And so I can think about that and back this up using a retrosynthetic analysis. Retrosynthetic arrow. And back this up to what? See if you can back it up. What would be the 2 reacting molecules to provide terbutylene? Keep it in mind, we're exploring the use of epoxides. We would take this sort of diphenol, I think it's called resorcinol, go back to that epoxide and react it with, it's a butyl group, that's where the terbutylene name comes from, this nitrogen, but that's going to be an NH2, right? Neutral amine. Okay. And so these two would react if these came forward to give that product. Answer is yes, because this would be a good nucleophile. All right. We would attack which carbon of our proposed epoxide? The right, less substituted. And so attack here, right? I'm not going to show full mechanism because I don't want to write all over this, but that would be it's going to be the aromatic ring. I'll just abbreviate that. We can't abbreviate phenyl. Phenyl would be just a plain benzene. This has more than just a plain benzene, but I can abbreviate it as aromatic. And then here, the nitrogen with the tert butyl. And this has got two H's here. The nitrogen is positive. Okay, nucleophile carbon, and then what happens here? This is, okay, I'm not showing full mechanism, but I'm showing this doubly charged intermediate proton transfer, okay? And proton transfer is going to take one of the protons and essentially it's going to end up on the oxygen, all right? And that would give terbutylene, and the nitrogen now only has one H, because one was transferred to the oxygen anion. So you got to kind of recognize what's going on there. And so this is how we can make terbutylene from reacting a strong nucleophile with an epoxide. Now the directions here said starting with an alkene provide a synthesis of terbutylene. Well, keep in mind, how do you make epoxides? We can go back and we can get that alkene, which is what we were asked to start with, an alkene, because we know coming forward we would react this alkene with something like MCPBA, a peroxy acid. These phenol groups are not going to cause any problem here. Alkene converted to the epoxide, and then react the epoxide with the, it's actually called tert-butylamine, and we would get our product here. Okay, so we did a little retrosynthetic analysis, thinking about how can we go backwards so we can figure out where to start. Sometimes the instructions may tell us what type of functional group we need to start with. Very often that will be the case. Okay, we'll do some more synthesis of epoxides over here. I'll go ahead and show you. Think about these here. The first one we've not covered chemistry yet to make a carboxylic acid, but the second one here you should know the chemistry, and you're asked to synthesize this compound starting with bromobenzene. Okay, so you can think about that. I'll go ahead and give you a little glimpse. We want to consider going backwards, retrosynthetic analysis. And we have an ether here. It's the main functional group, and we know how to make ethers. So we could propose going back to maybe, just going to abbreviate that benzene ring as phenyl. And typically, okay, we want to work back to just the benzene ring with a bromine. One step at a time, though. We went back to this alcohol. Okay. Cleave the ether. Could we come forward Yes, we would react that alcohol with maybe sodium metal, and then we're just doing a Williamson ether synthesis. Now we need an ethyl, maybe like ethyl iodide. All right. Well, let's keep going. Can we keep going backwards? We have an alcohol here. How do you make alcohols? Well, we'll learn there are actually many ways to make alcohols, but keep in mind kind of what we're doing here. It says using epoxides, kind of giving you some neon lights here. And reactions of epoxides give alcohols, OH groups, right? Reactions of epoxides typically leads to OH groups, and we call those alcohol groups. All right. We even said reactions typically give carbon-carbon OH, an alcohol group. Here we go, an alcohol group was made. Nucleophile carbon-carbon OH, can we recognize that? Leave this to, what about something like phenyl magnesium bromide plus 2-carbon epoxide? And indeed, if we come forward, these two will react to give this after H plus workup or water. Okay. And then we can go back. How do you make this Grignard? Well, that's going to be bromobenzene. And we would react this with magnesium. All right. Now you'd probably use ether or THF, but you don't always have to show solvents in your synthesis. You certainly could if you want. I did not show it here. So there you go. There's a synthesis of this molecule starting with bromobenzene. React with magnesium, make Grignard. React the Grignard with this ethylene oxide. After workup would give this alcohol. And then we would get, we could do a Williamson ether synthesis and alkylate it to make the ethyl ether. Okay, think about the others, but we've not covered chemistry up there yet. Think about the ones below here. Okay, down here starting with this alkene called styrene. All right. See what type of questions come up with multi-step synthesis. Okay. I may do, well, let's see if we got time to do polymerization here. There's a variety of miscellaneous handouts in this packet. But let's look at polymerization of epoxides. All right. Epoxides are prone to polymerization, and indeed there are some epoxy glues which when you work with them, you mix them and they polymerize on site into a hardened glue. If we take ethylene oxide, we can actually polymerize it. Let's see how that might happen if we use hydroxide. Okay. Base, aqueous base. Now this will react. It's symmetrical, either carbon, it doesn't matter. All right, kick off the oxygen. That's going to give this here, right? Now there's water here. We said aqueous. This could protonate, all right? And if it did, you would just get this product here, and we would call that a monomer, because it's just one molecule reacted. You see how we get the monomer? But instead of it just protonating, what if it reacted with another molecule? And this is how you do polymerizations. All right? Because this can act as a nucleophile, attack here, kick that off, and that would give OH, oxygen. That's bonded to that carbon, that's bonded to this carbon, and then the oxygen leaving group is on that carbon. A lot of times I see students put the oxygen leaving group on the same carbon that this oxygen attacked. No. This oxygen leaves that carbon, but it's still bonded to the next one. It leaves that carbon, but it's still bonded to the next one. Got to pay attention to all the fine details, or you'll end up getting things wrong, right? Okay, gives that. Well, guess what this can do? All right, lone pairs, well, it can react again. And what does that give? Okay, boom, 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 oxygen, boom, boom. I'm going to draw it zigzag, oxygen. Now this oxygen is bonded to carbon. Gives that, yeah. We can add all the lone pairs. And what can this oxygen anion do? Well, it can keep going. Somebody stop me. Till this becomes like a million atoms long. It becomes a polymer. How do we show a polymer? We show the repeating units. After the H, we have O carbon carbon. O carbon carbon. O carbon carbon. If you keep going, O carbon carbon. And so that is going to equal an H O carbon carbon yeah, I didn't draw that right. Let's try it again. H O carbon carbon. Let's draw something else here, but let's cut it off. We're not going to define what's there, and let's here. That's the repeating unit. After the H, O carbon carbon, and then what's coming off of this carbon? O carbon carbon. This just repeats, and we can just show an N, which means number. Okay. So this would be shown something like this. Now here I showed it a little bit differently, but is it the same thing? Basically I have the repeating unit in brackets, O carbon carbon. I showed some additional to it. This sort of assumes that the end is going to pick up an H. Indeed, eventually this can pick up an H, and you'll have OHs on both ends. Or maybe not. Sometimes polymers are rather undefined. There's different ways to show it, but consistent here is in the parentheses is the repeating unit of O carbon-carbon. And these polymers that come from epoxides tend to be glues. Originally sticky, they'll harden, and they will act as a glue. And you can actually buy some of these types of epoxy glues at like Home Depot. Okay. A miscellaneous topic here, thioepoxides, intermediates in mustard gas. Okay. Very toxic. What happens is the sulfur can act as an internal nucleophile and kick that off by SN2, and that forms a thioepoxide. Sulfur instead of oxygen, and the sulfur is positive, very reactive. And now nucleophiles come in here and kick that back off. This is driven by entropy, the molecule breaking apart. But when it breaks apart, it forms a very reactive electrophile. And nucleophiles in your body, such as DNA or other biomolecules, can then react with this reactive intermediate and cause lots of damage to the body. Your body also has water. Water could react. Okay, in that case, it's going to release HCl. You should see how. Okay, here's the Cl, and then you release H+. And if you start breathing this and releasing HCl in your lungs, you're going to have problems. So, understanding how mustard gases are toxic, you see similarities to epoxide chemistry, except it's a sulfur. Okay. We'll look at some of these miscellaneous handouts in class if we have time. One of them is an epoxide reaction worksheet, which is very good. Okay, it actually has a puzzle. Was the sodium atom certain that it had lost an electron? You can answer that by filling in down here. Each correct answer has a letter associated with it. Okay, epoxides have lots of applications. Okay. It's kind of up to you to, if you're interested in these important applications, we can discuss as you would like. Okay, read a little bit about to orient yourself. Biosynthesis of cholesterol involves an epoxide. Okay. Squalene epoxidase, that's an enzyme, you know. You can look these things up on the internet, Wikipedia. Epoxide here. You see epoxides lots of places. There's also an epoxide worksheet in the back. This did not make it into the workbook. The next edition of the workbook will include this. And so there are some extra problems from me. I also provide an answer sheet. I put it in upside down so you won't actually accidentally look at it. Okay, guys, that finishes up the epoxide handout, but there's plenty to be looking at and asking questions about.